Hello Honor Chem students. A brief video here to talk about self-ionization. That's when water can dissolve itself. So here we have liquid water molecules and a small portion, and I mean this is very, very tiny amount of water that will do this, but as you look here in your bottle of water or your glass of water, whatever it is that you may have, there is a little bit of what we call auto-ionization or self-ionization going on. And what is happening here is that these species right here, so when we look at the water molecules, and they actually do exist in a liquid phase, so I'm going to put these as liquid, okay? So these are liquid. They will dissolve into where one of these hydrogen ions right here, the proton, will get transferred to the water molecule and they will become aqueous. So both of these species would be aqueous, and that's what we call self-ionization or auto-ionization, okay? When you can see here what we have is that two water molecules, this hydrogen will get dissociated, okay, to the other hydrogen. So that sounds like a bronzed-telluric acid, right? Here water, this water is acting like a bronzed-telluric acid, and it would be connected to, right here, the conjugate base. So this is what it becomes. It would give up one of its H's and it would become an OH minus, a hydroxide ion. This water molecule will act as a bronzed-telluric base and accept a proton from this one. So it becomes a conjugate acid. And that is this term, that is a definition of what's happening there. It's called being amphoteric. And an amphoteric means that a substance can act as either an acid or a base. So water is amphoteric because it can act as both the bronzed-telluric acid and it can be a bronzed-telluric base. Just to give you guys another example of something that can be amphoteric, it would actually be something like the hydrogen sulfate ion. So if we look at that, it can gain a hydrogen and become H2SO4. Okay. And it can also lose a hydrogen. So we can have HSO4 minus, the hydrogen sulfate ion, losing that and becoming an H plus here and a sulfate anion. And so that would represent another species that could be what we call amphoteric. Okay, so and this is an important piece, and you may have heard this in the earlier video, is that we can actually keep track of the hydrogen and the hydroxide ion concentration in aqueous species by understanding what we call the KW. And the KW right here is a special KEQ. Okay, it is W, which stands for the ionization constant of water, and it is defined as the concentration of the hydronium ion times the concentration of hydroxide ion, and it will always have this value of 1 times 10 to the negative 14. So this is a good reaction to know, okay, equation to know. The KW, which I'll just commonly refer to as the KW equation, is equal to, the KW would be equal to the hydronium ion, or you could say hydrogen ion, times the hydroxide ion, and that value will always be 1 times 10 to the negative 14. So when these two values are equal, they have to have a value of 1 times 10 to the negative 7. And that might give you a little clue on something that we're going to learn in the next lesson about pH. This is related to the reason why the pH of water is 7, is it's because its hydrogen ion concentration is 1 times 10 to the negative 7. But we'll talk more about that tomorrow. Okay, so if we know either, and remember this bracket means concentration and molarity, if we know either the hydrogen ion concentration or the hydronium ion concentration or the hydroxide ion concentration, we can calculate the other. So here's an example. calculate the hydroxide ion concentration in a solution in which the hydrogen ion concentration is 1 times 10 to the negative 8, and I should have a unit behind there. So if we were face to face, you guys would all be saying, oh, Mrs. Snyder, you messed up. Yep, I'll make that as molarity. So 1 times 10 to the negative 8 molar. And then I'm going to ask you, is this solution acidic, basic, or neutral? So to do this work, what we end up doing is we take the Kw equation, which we know is 1 times 10 to the negative 14 times the hydronium ion concentration times the hydroxide, and then we plug in what we know. We know that the hydronium ion concentration, which is the same as the hydrogen ion concentration, is 1 times 10 to the negative 8, and then I'm going to solve for the hydroxide ion concentration, and I get 1.0 times 10 to the negative 6 molar. That's my OH concentration, where my H concentration, my hydrogen ion, is 1 times 10 to the negative 8. Which one's larger? And I say that to you guys because sometimes kids get mixed up. Remember, this is a negative sign here. So the one that you have more of is the hydroxide, because this is a larger number than this number, right? So the hydroxide is larger. So that means this solution is basic, okay? And how do we know that it's basic? Well, if you have more hydroxide or hydronium ion or H plus ion than hydroxide, then we say the solution is acidic. If you have more hydroxide than you have H3O plus, we say the solution is basic. And if these two concentrations are equal, then the solution is neutral. Okay? So, your homework tonight, or the work you should do to practice this, will have some problems like that using the Kw equation, so make sure you know how to do that. And to prepare you guys, there's also one little other kind of glitch that you have to kind of watch out for, and that is determining hydroxide ion concentrations when I give you a solution like this, okay? Well, if we're going to do a problem like that that says determine the hydroxide ion concentration in a solution that is 1 times 10 to the negative 1.0, times 10 to the negative 2 molar barium hydroxide, what I want you guys to consider is that you want to write the dissociation equation for this, because this has a little bit of an issue here for us. So I'm going to write this equation. I'm going to try writing the equation. Barium hydroxide is going to dissociate into barium ions with the +2 charge. Here's my +2 charge. And I'm going to have 2 hydroxide ions. Do you guys remember this? So if this is 1.0 times 10 to the negative 2, the barium ion concentration is also 1.0 times 10 to the negative 2. And this concentration is going to be 2.0 times 10 to the negative 2. That is because for every one of these that dissociate, there's 2 hydroxides, which we're showing right here. So my hydroxide ion concentration is, negative 2, is actually 2.0 times 10 to the negative 2. That doesn't make any sense what I did there. That should just be a -1 there. Sorry. So let's fix that here. I'm living on the edge. I'm going to try erasing just, oops. So we'll go back here and we're just going to put a negative sign there. So that hydroxide ion concentration is 2.0 times 10 to the negative 2, and the unit I put behind there is molar. So sometimes then, if I'm asking you what's the H plus concentration, or do you guys remember this is the same? These two things mean exactly the same thing. So what is the hydronium ion concentration or the hydrogen ion concentration? You're going to get that done through the Kw reaction, which we know this to be true. There's a bit of a lag in my pad. So here we're going to go with this. This is 1.0 times 10 to the negative 14th. This is what we're solving for. And the hydroxide you'd put in as 2.0 times 10 to the negative 12. Or sorry, 2. And when you solve for this, you should come up with the hydrogen ion concentration being 5.0 times 10 to the negative 13 molarity. So that's how you do problems with the KW equation. Good luck. See you next time.